Hi everybody, we're going to go through the Python tutorials and we're going to start with the 60-minute blitz. And in this series, I'm going to be looking at the Pytorch tutorials and learning them. I have already some experience with Pytorch in some projects that I look up in GitHub and I run in my computer, and some projects that I serve in servers, but I never gone through all the basic stuff and the really core technologies that Pytorch has. So we're going to go through this together. Hopefully this is useful for you, or you gain some encouragement to try by yourself. So yeah, if you have any questions, please tell me in the chat or in the comments if this is a video. And yeah, the idea is to be learning in a community and all together. If anybody has any questions, please do make them. All right, so we're going to start with the Pytorch rates. I have a collab here and I have the Pytorch tutorials. Oh yeah, the music. All right, there you go. All right, that's it. Okay, so as I said, the idea is to be learning together. I'm going to be reading what is in the tutorial, taking notes, searching useful things that I might not understanding, or I feel like it's useful to note in the collab. This collab is going to go be in the description, hopefully, and also I'm going to make a standalone blog post for this, so it looks maybe better. All right, awesome. So what is Pytorch? Pytorch is a Python-based scientific computing package serving two broad purposes: a replacement for NumPy to use the power of GPUs and other accelerators, and automatic differentiation library that is useful to implement neural networks. All right, so let's copy that and make it into the notebook, and let's continue. Goal of this tutorial: understanding Pytorch's tensor library and neural networks at a high level. Train a small neural network to classify images. Okay, so make sure you have the Torch and Torch Vision package installed. Yes, we have. We are in column. I didn't connect the PM, so we do that. And we're going to see 4 articles or tutorials. The first is Tensors, a gentle introduction to Torch Autograph, neural networks, and training a classifier. Awesome. I love it. Let's go for Tensors. All right. Any questions so far? I think that is pretty easy stuff by now, no? I was drinking a little water there. So, tensors. Tensors are a specialized data structure that are very similar to arrays and matrices in Pytorch. Use tensors to encode the inputs and outputs of a model, as well as the model's parameters. Tensors are similar to NumPy ND arrays, except that tensors can run on GPUs or other specialized hardware to accelerate computing. If you're familiar with ND arrays, you will be right at home with the Tensors API. If not, follow along this quick API walkthrough. Alright, so let's import this Torch. Alright, and run that, Shift Enter, and awesome, we run that. Tensors initialization. Tensor can be initialized in various ways. Take a look at the following examples. Directly from data, tensor can be created directly from data. The data type is automatically inferred. Okay, let's note that. data type is automatically infer when creating tensors. So data, and we have an array of arrays here. 1, 2, and 3, 4. Let's make it pretty. X data, torch, tensor, data, and run that. Awesome. Let's see. From NumPy arrays, tensor can be created from NumPy arrays and vice versa. See bridge with NumPy. Okay, let's take a quick look of this. So we are, this is ahead of us. All right, let's take a look at this variable to see what's up. I have a tensor of 1, 2, 3, 4, so it's like a matrix, right? I hope the missing is not too high. Maybe I can lower. Okay. All right, where were we? From NumPy arrays. Okay. Tensor can be created from NumPy arrays and vice versa. So let's create a NumPy array. Data and X, no problem. NumPy array. Torch from NumPy. All right, remember that. From NumPy. All right, awesome. And let's display this, and we have the same thing. Great. From another tensor, the new tensor retains the properties, shape, data type of the argument tensor unless explicitly overridden. So we have here once equal to torch dot once like x data. Once like copies the data of x data is another tensor. And we're going to print the tensor. Let's see. One thing that I learned from other languages that I sort of learn, right, is that, I mean, I could go ahead and copy this, right? But if I do that, it's not going to be in the memory. I need to physically do something or write it word by word. So in my head, I tend to remember this more. I learned this in a book called Learn Python the Hard Way. It's all of that. It's like in the beginning the book says that to you, that you need to write all of that you say, that you see in the book, and don't copy, so you can learn, right? So that's why we doing that here. Now we doing a random like. So right, so in this line we are taking the structure of X data and we are making it random, right? And we are overridden the data type of X and making it a float. Now we are printing it. F. Again, if you have any questions, please, of any type, right? I mean, I can tell you if I can't answer that, but go ahead. So what we have here, so here once like takes the structure of this tensor and make it all once, and this round like takes the structure of X data and make it all random. That's great. We have the same thing here. Now we see that with random or constant values. Shape is a tuple of tensor dimensions in the function below. It determines the dimensionality of the output tensor. All right. Let's take a look at that. So shape is equal to 2, 3. And notice that there is an extra comma here. Maybe they talk about this. I've seen this in other projects, but I don't know quite what it does. Tensor. So let's write this again because I didn't quite. It's a tuple. Shape is a tuple of tensor dimensions. In the function below, it determines the dimensionality of the output tensor. Alright, that's great. So once tensor equal to torch, once shape. So we're going to have a lot of zeros. I can type torch, zeros, shape. Alright. I'm going to copy the parents, right? Because we are not learning that much by typing them. I have here 2 by 3. So this is columns, and this is not the other way around. This is rows, and this is columns. So let's note that because I think it's important. So in this example, this is rows, columns, and the third one is like, how would the third dimension is called? Columns, rows, I don't know. Let's put a stack here. This doesn't exist, but we could make this like to see what's up, right? Let's go through 2. So it's going to go 2 by 3 and another one behind this. But of course, this is there is not 3 dimensions here, so this is the first one, and this is the second one after that, and similar with this one, and similar with this one. I'm going to take a little bit more water. Oh, I young the mic there. All right. What do we have here? Tensor attributes. Tensor attributes describe the shape, data type, and the device on which they are stored. So we have tensor, torch 1, 3, 4, and we have tensor shape, tensor D type, and tensor device. And we see that the tensor shape is 3, 4. The tensor data type is a float 3, 2, and the device is stored in the CPU. We can also store in the GPU. We might see that just here. Tensor operations. Over 100 tensor operations, including transpose, indexing, slicing, mathematical operation, linear algebra, blah blah, are more comprehensively described here on the docs. So torch, tensors. There's a bunch of things here. We might take a look at this at some point. Maybe doing a project. But it's alright. So we move our tensor to the GPU if available. We might have a problem here because I didn't. I I didn't run with. So going to restart, or this is going to take a second and execute again this. All right, no problem. I'm going to write if torch.CUDA is available typing and speaking is hard, equal to tensor.to CUDA. So we are sending the tensor to the GPU doing tensor.CUDA. What happened here? Oh, I did an oops here. So if we go to tensor.device now, what's going to happen? You can check the GPU here. So we're using 60%. What? We're using nearly a gigabyte for a 3x4. Okay, maybe some other things going on there. We got device here. We see that it's CUDA. Awesome. Now when we try out some of the operations from the list, if you're familiar with the NumPy API, you'll find the Tensor API ways to use. What we can use here? Right, let's see. Let's do a classic one. I mean, normal. Is it? So let's see. It was normal that way. Ooh, no. Interesting. Let's see. Transposing, indexing, mathematical operations. Let's click. What? What happened? Let me in. Well, that worked. Let's continue with this. Standard NumPy like indexing and slicing, right? So if we're continuing, let's see here. Into add a text and triple and do tensor tutorial. So we can hide it and make another one when we go to the next one. All right. So we have here tensor equal to torch 144 tensor. So here, where we are doing equal to 0. Let's print the tensor here first, and then we print the tensor again. As we can see, we are selecting the first column. I mean, the index 1 column. That is the second one. We're going and we are storing a 0 there. Nice. So joining tensors, you can use torch.cat to concatenate a sequence of tensor along a given dimension. See also torch stack, another tensor joining operation that is subtly different from torch cat. So we can use this 4x4 t1 equal to torch.cat. We're making another array of tensors. in the dimension 1. All right. Print T1. Oof, okay. So what do we have here? Exactly like that. So we concatenate them in the first dimension, and we put one 3 times over using the tensor. So here we have 4, 4, 4, and 4. Great. Let's try like the 0 dimension. So we concatenate in this direction, in the row, in the columns. I don't quite understand this. If we go outside the range, it's going to be an error. The measure of a range expected to be in a range of -2 to 1. We go to, we can do -1. Oh, we reverse it, isn't it? That's great to know. That's great to know. Let's put here -1. Multiplying tensors. This computes element-wise product and the alternative syntax. Element-wise. But it's not the matrix multiplication. Element-wise is not the matrix multiplication. Let's copy this because printing. Well, yeah, it's random things. So, I mean, it's 1. So 1 times 1 is 0. Let's see. Here's the matrix multiplication. This computes the matrix multiplication between 2 tensors. So, matrix M equal to tensor.matmu tensor.t, and the t is the transpose. Yes, it's a transpose. So multiplying this by this. The alternative syntax is that matrix M underscore tensor times tensor.t. Right, let's see if this works. Awesome. This is the output. 3. Great. Well, let's print it, right? Print matrix M. Print matrix. It's the same, but you know. Wait. In place operations that have underscore suffix are in place. For example, x.copy underscore y x t underscore, we change x. Going to drink a little bit of water. In place operation saves on memory, but can be problematic when computing derivatives because of an immediate loss of history. Hence, their use is discourage. Okay, let's keep that note. And print tensor slash tensor.add. I'm burping a lot. Let's see. Well, it's the same, right? But we add 5 to all of this, so this is useful to note. The add operator. Awesome. Now let's see the bridge with NumPy. Tensors on the CPU and NumPy arrays can be shared their underlying memory locations, and changing one will change the other. Tensors to NumPy arrays. So we have t equals to torch once 5 5 print oops the NumPy version. The same thing, right? But this is an array and doesn't have tensor, so we can do whatever we want here. Oh, that's not supposed to be there. MD through erase that. Oh, so if we do t add 1, but we do it in place, and when we print t and we print n, it's going to change in both directions. That's good to know. Let's see now. NumPy arrays to tensors, the other way around, right? Didn't we do this yet? I think we do this in the beginning. Torch from by n, and we have that. NumPy changes in the NumPy array reflects in the tensor. So in both, I joined the mic. So in both ways, the operation reflects. So we have np dot add n 1 out. I don't know what this means, but we print it. And we have that. Did we do it right? Oh, I didn't print it here. Well, let's believe it. Awesome. I think we finish the tensors basic. So great. We saw how to create, here, look for NumPy. The difference here, we're seeing that in both ways the operation reflects. Right. Awesome.